Hello, Ms. Heaton signing in to talk with you about buffer solutions. This is the second screencast in our part 2 of the acids unit. Hopefully you have already watched the common ion effect screencast because we're going to be building on that idea today when we talk about a buffer system. This is in your book, chapter 16.6. It goes through the basics but not the more intense calculations that we're going to get to do. So we're going to talk about kind of the concept of buffers and then do some calculations. So make sure you have your calculator nearby. So first of all, let's talk about what a buffer is. Maybe you've heard that word before in a science context, maybe not. Basically, in chemistry, a buffer solution is a solution which does not change pH very rapidly. An example of something that is not a buffer is pure water. If we were to add acid to it, if we added like 0.1 moles of acid to it, the pH might go from 7 to 2 just by adding a little bit of acid. Now, remember, the pH scale is logarithmic, and so that's 5 orders of magnitude more acidic. So that would be 100,000 times more acidic. So it does not really resist a change in pH. On the other hand, blood is a buffer system, and we'll talk about exactly what's in that later when we do a calculation. If we added acid to blood, the pH goes from 7.4 only to 7.3. So if you do the math there, that's only about 1.25 times more acidic. That's really good because if you can only survive in certain pH ranges and somehow acid gets into your blood, it's really good that the blood is able to contain that in a sense by buffering the pH and preventing it from spiking or dropping really rapidly. A buffer system contains 2 components. Typically, it contains a weak acid, which we'll call HA, and its conjugate base, which we'll call A-. Remember from our earlier acid discussion, an acid like HA might break into H+ and A- ions, so it's the acid and then its conjugate base. Now, we could also have a buffer system that is made of a weak base, which we could maybe call B, and its conjugate acid. So it's a conjugate acid-base pair. Typically, like I said, we'll deal with ones that are acids, but you could also have a buffer system based on a base. Here's an example of a buffer situation that might make a lot of sense. You know, here at York, we do a lot of running. Lactic acid is produced by your muscles after short energy bursts, and lactic acid is this compound right here, and its conjugate base would be the lactate ion. We'll do a calculation here in just a minute involving that, but you know, if you had both lactic acid and lactate ion mixed together, that would be a buffer solution that would resist a change in pH. You could kind of think of it like a double-edged lightsaber. What the buffer will do is either send out the weak acid component or it'll send out the conjugate base component in order to tackle whatever acid or base we add to the system. So it's kind of trying to undo or neutralize whatever is added to that buffer solution. So if you add acid to a buffer solution, let's start with this as our kind of stress out the buffer system situation. If we add acid, let's think for a second. Which part of our system, our buffer system, will we try to send out to neutralize it? Well, if we're adding acid, acid reacts with base to kind of cancel it out. So if we add H+ to our system, the conjugate base is going to get sent out to neutralize it. So that would be the C3H5O3-, the lactate ion. So here's the key idea. This is what you need to write down. If you add an acid, like H+ ions, the conjugate base will react to completely neutralize it and turn it into the weak acid component. Because once that conjugate base gains the proton, it is now like the weak acid. Like if the lactic acid gains a hydrogen, it becomes like lactic acid. On the other hand, what if we added base to the buffer solution? Well, base is OH-, and so it will probably react with the acid. And so the acid component of our buffer system will neutralize it. So what might that reaction look like? Well, if we send out OH-, the weak acid, the HC3H5OH, might react with it, and what would be left behind? Well, the H2O would form when the hydrogen from our acid reacts with the OH-, and it would leave behind the C3H5OH-, the conjugate base. So that's kind of how a buffer system captures or neutralizes whatever is thrown into it to keep the pH from changing too much. Let's talk about calculations. There are 3 kinds of buffer calculations that we might ask you to do. The first is just kind of common ion calculations, basically to calculate the initial pH of a buffer solution before you add anything to it. Then we might ask you to calculate the pH after you add some H+, or after you add some OH-. So let's just dive right into an example so you can see how this is done. As I mentioned earlier, blood is a buffer system. It contains carbonic acid, H2CO3, and the carbonate, well, I forget exactly what you call that, I think it's bicarbonate, the HCO3 minus ion. So let's say that we had a 1 liter buffer solution and it had 0.3 moles of the acid and 0.2 moles of the conjugate base. Let's label those acid and conjugate base just for clarity's sake. The Ka is given to us, so let's find the pH of this buffer solution. So we're going to be using the Henderson-Hasselbalch equation. That's such a fun name to say. So the equation for that is that pH is the pKa plus the log of the conjugate base's concentration over the acid's concentration. So what we'll do is just plug in the numbers that we know. So the pKa is the negative log of the Ka, which is 4.4 times 10 to the negative 7. Then we'll add that to the log of the conjugate base concentration. Ooh, now notice that these are given in moles. We do need to convert them to molarity. Oh, but we're in luck because it's just 1 liter. So we would put molarity of the conjugate base, H2CO3, on top, and molarity of the acid, H2CO3, on bottom. And when you type that into your calculator, you should get 6.36 plus negative 0.176, which turns out to be 6.18. So this blood buffer system has a pH of 6.18, so slightly on the basic side. So the next kind of calculation you might have to do is figure out what the new pH would be when we add something like an acid. What if we added, say, 0.07 moles of H+? Now, what this is going to cause us to do is have to make an ice chart, because what we'll do is we'll take that acid and we'll react it with something from our buffer situation. Now remember, does acid act with the conjugate base or with the weak acid? Well, we said it will react with the conjugate base, because acids and bases react to neutralize each other. So this will be our reaction. So we'll make our ice chart. And here, E doesn't really stand for equilibrium, it more stands for end. But we approach it the same way. Fill in what you're starting with. Well, we put in 0.07 moles of H+, and initially we had 0.2 molarity of our, oops, I should have said molarity for that. Again, we're still dealing with 1 liter. So 0.07 molarity of H+, 0.2 molarity of the conjugate base, and 0.3 molarity of the carbonic acid. Now, our change rho will be done in the same way as well. Every time we run the reaction, we'll use one of those and make one of these. Except, wait a second, what's going to happen? We're going to react until all of something is used up. We are going to use our either conjugate base or acid to completely neutralize whatever either acid or base we've added. So we have to end up with 0 of that at the end. 0 of something at the end. So in this case, we're going to use up all of our H+, because that's our smallest amount. So all of these will be 0.07. So this will be 0.13, and this will be 0.37. Okay, so those are our equilibrium or end amounts of each chemical, and we can plug that into our Henderson-Hasselbalch equation. So the pH, again, is the negative log of the Ka plus the log of Cb over A. And so we'll just plug in, well actually we could probably still use the same pKa, because it's the same Ka as before. And then we'll plug in, let's see, now our concentration of the conjugate base is going to be 0.13. And the acid will be 0.37. So that will turn out to be 5.90. Okay, so let's check and see if that makes sense. Did the pH go down slightly when we added acid? Because, acid should make the pH drop a little bit. And that's exactly what we saw. The pH didn't change dramatically, but it did decrease a tiny bit. Okay, we're going to approach base now. This is the third kind of calculation. Adding a base like OH minus, or something that contains OH minus, let's say that we added 0.15 moles of that. Again, you're going to be making an ice chart based on the reaction that occurs to neutralize that OH minus. So if we add OH minus, which part of our buffer situation, our buffer solution, will be sent out to attack it? Will it be the H2CO3 acid, or it will be the conjugate base HCO3 minus? Remember, it will be the acid, so we'll send out the H2CO3. And let's think about how that will react. Well, if this is a base, it's going to gain a hydrogen, so that would be H2O. And this is our acid, so it will donate its hydrogen, leaving behind just HCO3 minus. Only one hydrogen can be used at a time. You will never lose two hydrogens at once. Our initial amount or concentration of OH minus is 0.15. For the H2CO3, it was 0.3. And for the HCO3 minus, it was 0.2. Remember, water is a liquid, so it won't count. And then we will need to fill in our change row. Whatever we have the least of to begin with, typically, will be what we use up completely. So we'll use up all of our OH minus, and we will turn it into HCO3 minus. So we'll have 0 of the hydroxide at the end. We'll have 0.15 molarity of the H2CO3 and 0.35 molarity of our conjugate base. Then again, we'll just plug that into our Henderson-Hasselbalch equation. Who knew that was going to be so useful? Plus the log of the conjugate base, which was this one, over our acid. So it'll be 0.35 over 0.15. So that'll be 6.36. Whoops, I don't have that written down. But I do have the final answer. I think it should be 6.73. Double check my math, make sure I did that one right. Does that make sense? When we added base, our pH went up a little bit from what the buffer solution by itself was. Yeah, the buffer by itself was 6.18. So by adding base, it went up a little bit, but not too much. Excellent. Okay, I got one more for you. I'd like you to pause this one. We'll write it down. Pause, try this one on your own, see if you can get to the right answers. Okay, here's the work for the first part, just finding the pH using the Henderson-Hasselbalch. Notice that this one's a little bit lower, more acidic in pH than our previous example. Here's the work for the second part, adding the acid. Notice that it will react with the conjugate base to make the acid. So your change row will be minus 0.2 and plus 0.2. So when you plug that into the Henderson-Hasselbalch, the pH goes down a little bit to 2.66. And finally, here is the work for the third part. In this case, we are adding hydroxide base. So it reacted with the acid to make our conjugate base, NO2 minus, and water, which we disregard because it's liquid. We started with 0.4 of the OH, 0.7 molarity of the nitrous acid, and 0.45 of the conjugate base. And then at the end, we had 0.3 of the acid and 0.85 of the conjugate base. So when you plug that into the Henderson-Hasselbalch, it goes down in pH, goes up in pH to 3.67, as compared to our initial pH, which was 3.03. Okie dokie, folks, that is buffer solutions in action. We will be practicing this more, but please send your questions to your teacher so that you can become the buffer master and know exactly which part of your buffer system to send to battle. Happy buffering.